Alright, so the problem that we're going to discuss today is polynomial queries, that is a CSES problem. So let's straight jump to the solution. So I'll be explaining the problem by using three queries. The first query is the operation one, that is in the question, that is in the range from 1 to 5. The second is from 3 to 3 and the third one is from 1 to 5. Okay, so this is how the segment tree is going to look for the current situation, and we have to add these values to all the nodes. Value 1 to 1, 2 to 2, and then 5 to 5. Okay, so this is the segment tree. So you can also use another type of segment tree in which we first expand the array to a power of 2, that is to 8, but this also works just fine. So in this case we have to update the values of the array in such manner. So yeah, so the idea behind this problem is that basically we are going to split each query into two halves. So how is that going to help us? So let's discuss that. So this query can be split into two halves, that is, first adding 1 to all numbers in the array, and then adding a sequence that is 0, 1, 2, 3, 4. So how is this going to help us? So in all the problems of range updates we have seen, for example, we have to add 7 to a range, then we have to add 6 to a range. So in all those cases we are able to join multiple queries into a single query. For example, we are at a particular node, so we have a lazy update on this node that we have to add plus 7 then plus 6. So these two queries can be combined, that is adding plus 13 to this particular range. So by splitting the query in this format, we can actually achieve this similar goal. Okay, so since we're splitting this, we also have to maintain two lazy nodes. So this node basically represents the sum in this range, basically in the subtree. This value basically stores the initial value, the sum of initial values of each range. I'll explain this later, and you'll understand that. And this node basically stores the number of operations or the number of queries that we have to do on this range. Okay, so this is the first node. We have a complete overlap. So 15, that is the sum of this entire range, will be added here. So this can be easily evaluated by using the summation of n, that is n into n plus 1. So the values of this node is completely updated, and we don't need to do any lazy updates. Instead, we have to do lazy updates on the children nodes. So how are we going to do that? Okay, so let's clear it. Erase everything. Oh. So this range is then broken down into two subtrees. This one corresponds to this node, and this range corresponds to this range. So since it is a lazy update, so the sum is not yet updated, so this will remain to 0. Now 1 corresponds to the initial value of the range or the other value that is to be added. So this 1 means that only one operation till now has been done or needs to be propagated down to this subtree, and the sum of starting values of all these ranges is 1. Okay, so you'll understand it later, I'll explain it later, but now just get the idea. And similarly for this node, so for this node the values that are added are 4, 1. So we store 4 in this place, and 1, that basically means the number of updates we have done or we have to propagate down. So 4 and 1. So I hope that these lazy values are clear to you. Now the second operation is that when we have to add 3, 3. Okay, so we have to add value in the range 3, 3. So for this node you have a partial overlap, so we'll have to go down. So this we go here, we have no overlap. Now in this case we also have partial overlap, but in this case we have some lazy values that we need to propagate. So now how is this sum going to be um, generated from these lazy values? So this one means that this one first needs to be added to all the values in this range. So this range is 1, 2, 3. So what we need to do is that we need to add 1 at all these places, and then we have to do one operation of this kind in which we are adding 0, 1, 2 to the entire range. So we can easily calculate the contribution of these two values, and this turns out to be 6. So these lazy values will make this value 6, and these both values will become 0 because all the lazy values have been propagated down, and then we need to propagate these two lazy values to the below, to the subtrees. So as mentioned earlier, the sum of this subtree of this node will become 6, and now the lazy values, these two lazy values need to be propagated down. So these values will be propagated in such a way. So as we can see, the lazy values were 1 1, but now they have become 3 and 1. So we'll discuss that later. 1 basically means that the number of queries that need to be propagated are 1. Okay, I'll explain this logic why this becomes 3 and why this remains 1. So this is basically we're updating the values, we're propagating the changes to this node. So 3 is the lazy propagation, and 1 is the value that is added in this query, and so the value or the sum in this subtree becomes 4. Alright, now the third operation. So in this operation, what we have to do is that we have to again perform a similar query of the first kind. That is, we have to add values in the range 1 to 5. So when we add the values in the range 1 to 5, this gives us a complete overlap. So we can just simply add the sum to this node 31, and but we also need to propagate these changes to the children node. So we'll discuss the propagation only in the right subtree just for educational purposes. So yeah, so we have to propagate some changes to this node. So this node corresponds to 4 and 5. So as you mentioned earlier, this is split into two halves. These updates refer to this, and these 4 and 5 update refer to this node. So yeah, so initially the previous lazy values for this node were 4 and 4, but now they are updated in such a way. Okay, so the new value, that is the initial value of the first node of this node, that is 4, is 4. So we add those, and this basically one means that we have another operation that we need to propagate down to the children node. So this is also added by 1. So in all the cases, whenever we're going to propagate, this will always be added by 1, and this will be added by the value of the first value of the range, or the update that is to be carried out. So this becomes 4 and 4, so this becomes 8 and 2. So what this 8 and 2 signifies is that we have to perform two operations. The first operation is that in this range, that is 4 to 5, let's suppose this is 4 and this is 5, you have to first add 8 to all the nodes, and then we have to perform two operations of this type, that is 0 1. So when we'll add these two values, we'll get values that is 8 and 10, and which is actually the value that these two nodes will have after performing all these operations. So basically we have divided each query into two query, and by that we are able to combine multiple queries into a single query, and that is basically the idea behind lazy propagation. Yeah, that's pretty much it. Okay, so just in case if you didn't understand how we are propagating down the values, so this is another part. I'll explain that here, and if you understood, then you can skip this part, and I'll add the coding part at the end of the video. Now, yeah, so yeah, let's take this example. Hmm. So you have to perform these two queries on this node, and this node stores a sum for the range 1 to 3. So these two queries can be combined into this lazy format. So it is a lazy node, the values are not yet updated, so the sum is still 0. 17 is sum of these two values, 17 and 10, and 2 is the number of queries that we have to perform. So yeah, so this can be split. So to calculate the value for this node, we can calculate the contribution for this value, and then for this value. This value means that we have to add 17 to all the nodes, and then 2 means that we have to perform, or we have to add the contribution of this series two times. So this series is in all the cases going to be 0 1 2 till width minus 1, where width is the width of this node. So width is here 3, that is 3 minus 1 plus 1. So when we add these two contributions, the values we get are 17. 17 plus 1 times 2, that is 19. 17 plus 2 times 2, that is 21. And these are the final values that we're going to get after carrying out the operations. And we can also cross check that these values, they do add up. Yeah, so this is how we are going to update a particular node by the lazy nodes that are still present on the node. The second part is how we are going to propagate the lazy updates to the children node. So as we can see, yeah, this was the lazy update for this node, then they are propagated back, and these are going to the lazy values for the child nodes. So we can clearly see that the lazy values for the left child node are going to be as it is equal to the parent node. So why is that the case? That is the case because the initial value for these two nodes is same, and what we are actually storing here is basically the sum of the contributions, or the sum of the values that are to be added to this first node. So basically this means that for example uh, let's say 70. So this means that this 70 is added to all these values, and the remaining contribution is done by the series that is from 0 1 2. So this 70 is basically the value that is added to this first value, and that value is then copied to all the values, and the remaining part is done by this series that we have. But in this case 3, for 3, the first value that is added to 3 is not equal to the value that is added to 1. Let's consider the series that we had. Let's clear it. So we had 7, 8, 9. For the left subtree, the first value was 7. But for the right subtree, the first value is 9. So in this case, for this subtree, we have to maintain the sum or maintain the values that are added to this 3 node. So that is why this value on 21, the value of this node is changed. And this is and we can get this value by basic mathematics. 21 here is achieved by doing this operation, that is 17 plus 2 times 2. 17 is basically the value that is added to the first node of the parent node, and for 3 what we need to do is that we have to add this extra value. So what is the significance of the extra value? 2 times 2, 2 means that the number of queries that we have to carry out, or the basically the number of queries whose values need to be propagated down. So that is stored in this node 2, and this 2 basically means the width of the left subtree. Okay, so why is this width important to us? Because important to us, for example, if this value starts with 7, then the first value that is to be added to the right node is going to be 7 times the width of this left subtree, that is 9. Similarly, if the value or the update on this node was 10, then the corresponding update to the right node or to the right subtree is going to be 10 plus 2, 12. So this is how we are going to calculate this lazy value on the right child. Yeah, that is basically how we are going to propagate the lazy nodes from the parent node to the lazy values from the parent to the children nodes. So this is basically the code that we are going to use to propagate values. I have added this part here just for explaining. Consider the case that we have a root node here, and these are the two child nodes, and it has some lazy values. So first part is to update the value of this particular node. So first we calculate the width of the parent node, that is n minus star plus 1. This helper function basically returns s of n, that is n into n plus 1 divided by 2, and lazy2 means the number of operations. I mean, this is lazy2 and this is lazy1. Yeah. So first we add the contribution of lazy2 node, that is pretty straightforward, and then we add the remaining contribution of the lazy1 node. So the contribution of lazy1 node is that we have to add the value to all the nodes in that width or in that node. So that is represented by this width value, that is the number of nodes in that subtree, and then we add the same value to all these nodes, and then we add that value to the parent, or add that value to the sum or the node. You get the point. So this is how the value of the current node is updated, and then we have to propagate these lazy values to the children node. So we update that here, and then after propagating the lazy values we set them back to 0. So as we can see that the updates for the left node are as it is, they are not changed, they're just added. But for the right node we have to do some simple mathematics that we discussed earlier. Yeah, so that is pretty much it, and then yeah, we'll just code it, and yeah.